Hello, my name is Vishal Chaudhary Meka, and I will be presenting the practical concurrent extraction engine tailored for hybrid fuzzing. This is a work done by Georgia Tech students and Oregon State University students and the professors. So, coming to the topic, there are many ways to find the security bugs, but the top most famous ones are fuzzing and concurrent execution. These are the two main things used to find security bugs. Both the fuzzing and concurrent execution have their own positives and negatives. Fuzzing is good for finding general inputs and it is bad for finding a specific input. Coming to concurrent execution, it is good at finding specific inputs, but it is bad at finding the state explosion. The hybrid fuzzing can combine both the fuzzing and concurrent execution to find the specific input but with the limited explosion. Talking about the hybrid fuzzing has achieved many great things, like won a third place in CGC competition, and it has also found some new crashes where they cannot be found by fuzzing or concurrent execution. The current model of the fuzzing cannot be used for the real-world problems because it has many problems currently, like it is very slow and cannot support systems calls, and also it is not effective in generating test cases. It basically runs very slow, and the work is also done very slow. So the QSYM can correct these problems by discard intermediate layer and use concrete environment to support system, and also it introduced the heucrites to effectively generate the test cases. The QSYM can be used for the real world problems because it has identified 13 bugs that were unknown in the open source software system before, and all the bugs are currently fixed, and all the bugs are hard to fix because of the requirement of the complex complex constraints. So this is how the hybrid fuzzing works. In general, as you can see on the screen, the program goes on to the basic block and it gets converted to the intermediate representation, and represent intermediate representation then generates the state fuzzing and can straight the constraint generate the test cases, and the test cases are sent back to the fuzzing. The intermediate the intermediate representation has a problem because of it the whole program is being slowed down, and because of that step all the other processing things, other steps after this step are also being slowed because of this. The QSYM overcomes this problem by directly sending the information from basic block to constraint, and it generates test cases and then to fuzzing coverage. This is the whole process, as you can see on the screen. If you have any questions about this, please comment down below. Even the state Even the state forking creates problems, so to overcome that they use the constraint environment modeling to separate the system so that the work can be done faster and more effectively. When the test cases are being generated, it also causes problems like test cases generates ineffective test case generation due to unsatisfiable paths that the system takes because of the time that is being taken, and it's not effective, like the QSYM. The QSYM solves these problems to by optimizing optimistic solving. As you can see, the test cases and constraints also have problem, so they're not satisfied, and because of this, they corrected this by the QSYM. And as you can see, the QSYM model, it goes from basic block to constraints to test cases and fuzzing coverage. This is the correct environment model and introduction level execution, which is the most effective way. So in the hybrid fuzzing system, the constraints model it's being blocked by complex logics where you cannot get the effective outcome that you want, and the system also takes a lot of time to process the whole thing and convert it into test cases. And the QSIM corrects it by constraints, it goes directly to the test cases, and the basic block pruning refers out and the test cases directly go to fuzzing coverage, and that's how the whole process works. The hybrid fuzzing in general, the performance is low and the system takes long time. The performance is overhead to especially the intermediate representation. The performance is overhead, and after this, the steps take too long to process the whole thing. The intermediate representation are good to make implementation easier because we can reuse the code as many times as we want for the architectures and provide architecture independence. And for example, it's the x86 and ARM and MIPS. The the incur significant performance overhead. The increased number of instructions 4.7 times VX need, and the other point is need to execute a whole basic block symbolically. Only need 30% of instructions need to be symbolically executed, which is basically you don't need to put that much input for the system to give you the most effective output that you want. And the solution is remove the IR translation layer because that's the main problem for the system because it is taking too much time and taking a lot of time for the next steps to process the whole thing. And another one is pay for the implementation complexity. And this is the graph. The QSYM reduces the number of instructions to execute symbolically. The drills take around more than 600K, where the QSYM takes four times less than that. It takes less than 200K to give you the best outcome. And another problem we have is state forking, which is incomplete environment model. So, and the solution. Another solution, the state forking can reduce the re-execution where no need to re-execute to reach the state, recover from the snapshot. The state forking for kernel is non-trivial. The forking process system is trivial. It saves the application memory. The register saves constraints. Also needs to also need to maintain all kernel data structures. For example, file systems, networks, memory systems, and etc. For this, if you combine the program state plus the kernel state, you get the state in Concolic execution where it's the same amount of memory for the program state and the kernel state combined. And the problem too we have with the state forking introduction problem is the kernel modeling, which is anger pros and cons. It has its own pros and cons. The small performance overhead, and anger supports only 22 system calls in Linux. The full kernel emulation, the S2E, which has its own positive things, which is completeness, large performance overhead, where it has more than 22 system calls in Linux. And the solution is the solution to use constrained environment instead of kernel state forking is the high re-execution overhead, instruction level execution, basic block pruning, and it'll limit constraint solving based on coverage from fuzzing. And the model's minimal system calls and uses constraint value. Only model system calls that are relevant to use interactions, example, a standard input file read, and other system calls. And the problem is the concrete environment result in incomplete constraints where you don't get the output that you want. Add implicity constraints without knowing semantic or system calls. The and some of this is one of the if statement that we have where you can see how it is being processed and the output that you get is the x equals use concrete value and y is the same where 1337 multiplied by 1337 That's what the y value that equals this. The y value is 1337. And here we have a problem with the test cases and constraints as well, because constraints push and create the test cases, which is ineffective test case generation due to unsatisfied paths, and also it is not effective. And this is the thing you can see on the screen, where the whole process of how it is being processed, where it's going to take longer time and you don't get the test cases. So this is the problem that we have. And all these breaches, and if these breaches are independent, the problem continues like this. So the best solution we have for this is combining the blocks so that they take less time to run and process things, and you're gonna get the best output, the best results that you expect from it. And the our decision solves only the last constraints in the path. Simply one constraint is high chance to pass the breach, which is the thing that we want. We want it to pass the breach and only waste small amount of time, so that even if the result is good or bad, we can just move on to the next one. If it is wrong, we can work on it and push it again. If it is correct, we can move on to the next one. The whole process happens in a very small period of time, which is very helpful. And in hybrid fuzzing, the fuzzing will filter out incorrect input based on coverage, where fuzzing is filtered out and the coverage is applied for the thing. And as you can see, the graphs for the solving helps to find more bugs, where you keep on solving. The red one is with optimistic and the blue one is without the optimistic. And the implementation, it's 16K LOC of C++ and Intel pin emulation Z3 constraint solving. You can get it from this link, as you can see on the screen. It's available in GitHub currently. And any evaluation questions, scaling to the real world software, you can drop them down in the comments if you have any questions regarding this presentation. And how would the QSYM compare to drilling, Weathering, and fuzzing would be is that comparing all these things with QSYM has the best outcome, best results currently in the market. So, and and these are the 13 bugs in the real world software that QSYM has found. And yeah, without QSYM, we would have never been these bugs would have never been found from the program that is open to the public. And this is the QSYM can generate test case. That fuzzing is hard to find, so this is one of the test case that is generated by the QSYM. And the QSYM with drill state-of-the-art hybrid fuzzing. The database is only 126 binary is and runs only on intense concline execution for 5 minutes where it removes the fuzzing and compares code with coverage to see how it is doing with all the coverage and all. And the QSYM achieved more code coverage than drill in most cases of CGC. QSYM actually won third place in the CGC competition. Also, among the 126 challenges, QSYM achieved 104 challenges more than the drill achieved. Drill achieved 18 challenges and QSYM achieved 104. So where QSYM is performing much better compared to Driller, and QSYM achieved more code coverage due to its better performance and it's taking less time to solve all the cases and all. To achieve new code coverage, 7 stages are required, as you can see on the screen. Add one user, add another user, login, send to message, and few more steps after that. QSYM can reach a stage where the driller cannot reach in the same period of time that is given to both the systems. The driller achieved more code coverage if nested breaches exist. Driller can find inputs and nest breaches by a single execution due to forks. QSYM requires re-execution because QSYM is not that better in this kind of field. And on the screen, as you can see, comparing all the programs, you can see that the QSYM has gotten the better result comparing it with all the other programs where they ran it for 5 hours. They ran all of them for 5 hours. Inject a hard to find bugs in real world software where fuzzing got almost 100% in three of the categories and of almost a 60% in the other one. And discussion and limitation: use of less accurate test cases. The QSIM uses less accurate test cases, requires less time, and it works effectively comparing it with other softwares that are available. And the implement status, it only supports the x86, x86 underscore 64. And the conclusion: hybrid fuzzing scalable to real world software where it has found 13 bugs, and the QSIM is also a better one under this output where state of the art hybrid fuzzing and other bug finding, and it's available in this GitHub link. You can get it, and thank you.